Imagine trudging through a foot of snow in your driveway, the bitter cold biting at your fingers. Instead of wrestling with a shovel or a clunky snowblower, you grip a flamethrower, its nozzle glinting with raw power. With a deafening roar, you unleash a blazing torrent of fire, and the snow vanishes in a hissing cloud of steam, leaving the ground bare in seconds. Sounds like a reckless, thrilling fantasy, right? But could this fiery beast actually clear your yard, or would it unleash a cascade of chaos, scalding floods, explosive fires, or even a runaway greenhouse effect that alters the planet? This isn't just a stunt for viral clicks. It's an electrifying journey into thermodynamics, combustion science, and human ingenuity that pushes the boundaries of what's possible. We'll dive into real-world data, crunch mind-bending numbers, and weave a story of fiery disasters and futuristic breakthroughs that keep you glued to the screen. From vaporizing snowdrifts to redefining how we conquer winter, this thought experiment blends hard science with jaw-dropping possibilities, sparking curiosity at every turn. Welcome to our channel, where we set ablaze the universe's boldest what-ifs with unmatched energy and depth. Let's torch some snow and see what burns or explodes. First, let's dive into the core challenge. What exactly happens when you point a flamethrower at a pile of snow? A flamethrower isn't your average tool, it's a powerhouse that spews burning fuel, like propane or napalm, at temperatures soaring to 1,900 degrees Celsius, hot enough to melt steel in moments. Snow, by contrast, is just frozen water sitting at 0 degrees Celsius, ready to absorb heat and transform through melting or vaporization. The physics here is deceptively simple. To melt snow into liquid water, you need 334 joules per gram to overcome the latent heat of fusion. To turn that water into steam, you need another 2,260 joules per gram for the latent heat of vaporization, plus about 418 joules to heat the water from 0 degrees Celsius to 100 degrees Celsius. Let's scale this up. Picture a driveway buried under a meter of snow, roughly 10 cubic meters. Now, let's anchor this wild idea in the current state of science and technology to see how it connects to real-world innovations. Flamethrowers and snow management aren't new, but combining them stretches the boundaries of what we know. Modern flamethrowers, like the X15 model popular among hobbyists, deliver 50 to 100 kilowatts of heat, projecting flames up to 15 meters. According to manufacturer specs from 2024, they're used in controlled burns for agriculture or wildfire prevention, where raw power outweighs the need for finesse. Snow removal, meanwhile, relies on a mix of plows, blowers, and melters. In cities like Buffalo, which faced 2-meter snowfalls during the 2022 blizzards, municipalities deploy gas-powered snow melters that process 100 tons per hour at 800 degrees Celsius, carefully calibrated to prevent explosive steam, per municipal engineering reports. These systems hinge on thermodynamics. Heat transfer depends on temperature gradients, and snow's low thermal conductivity, around 0.1 watts per meter Kelvin, causes uneven melting, creating hotspots that can refreeze into hazardous ice. DIY enthusiasts have experimented with propane torches for small-scale snow clearing. One viral video from early 2025 showed a 20 kW torch vaporizing a snowbank in seconds, but leaving a slick ice layer as melted water refroze without proper drainage. This mirrors our scenario. A flamethrower would obliterate surface snow, but could glaze deeper layers, turning your driveway into a skating rink. Combustion science adds complexity. Propane burns at 1,900 degrees Celsius in oxygen-rich air, but incomplete combustion releases carbon monoxide, a serious risk in enclosed urban areas, as noted by the National Fire Protection Association's 2023 data on fuel-related injuries, which reported over 5,000 incidents annually. High-heat technologies aren't science fiction. Industrial furnaces reach to 0 degrees Celsius for steel making, and plasma torches for metal cutting hit 25 degrees Celsius, according to materials science journals. Computational fluid dynamics, CFD models, used in rocket propulsion design, crunch terabytes of data to predict heat transfer in extreme conditions, like the steam explosions our flamethrower would trigger. These advanced simulations set us apart, offering precise insights over back-of-the-envelope guesses. A viral X thread from 2024 debated torch-based snow clearing, with engineers highlighting cavitation, risks vapor, bubbles in superheated water collapsing with enough force to erode steel, as seen in high-pressure pumps. Recent advances in burner technology, like those in GE's 2025 jet engine designs, show that adaptive nozzles can stabilize combustion at high outputs, suggesting precision is within reach. Real-world extremes reinforce this. Deep-sea hydrothermal vents, per NOAA's 2024 oceanographic data, spew 400 degrees Celsius water at 100 meters per second, sustaining life in crushing pressures, proving nature handles high-heat fluid dynamics in ways we're only beginning to mimic. The field is evolving fast from bio-inspired burners that mimic insect respiration for better fuel efficiency to AI-optimized heat sinks, analyzing vast datasets to prevent thermal runaway. The excitement surges, taming fire and ice powers everything from home heaters to space thrusters, and our scenario pushes those boundaries to the limit. What's the wildest heat-based gadget you've encountered? Drop your story in the comments. It might inspire our next fiery exploration. Building on this foundation, let's explore the future implications of mastering flamethrowers as snowblowers. What could this mean for technology, climate resilience, and human survival? By 2050, advances in materials science could produce flamethrowers that aren't just weapons, but precision tools. Ceramic matrix composites, capable of withstanding 30 degrees Celsius, as tested in aerospace labs in 2024, could craft nozzles that channel heat like a laser, avoiding the steam explosions that plague our current scenario. Imagine portable fireblowers clearing entire highways in minutes, using directional plasma jets inspired by fusion reactor designs. These devices could transform winter cities, replacing diesel-guzzling plows with compact units that melt snow into reservoirs, tackling water scarcity in arid regions. The International Energy Agency's 2025 report projects urban energy demand rising 40%. By 2040, fireblowers powered by green fuels like hydrogen, which burns cleanly at 200 degrees Celsius, could slash snow removal's carbon footprint by 70%, making cities more sustainable. On X, futurists are buzzing about adaptive flamethrowers with AI-controlled nozzles that adjust flame intensity based on snow density, preventing refreezing and optimizing energy use. These could extend beyond snow to disaster response, clearing avalanche debris, thawing frozen pipelines, or even melting flood ice in Arctic communities, saving lives where traditional methods fail. The implications reach into space exploration. NASA's 2024 tests of plasma thrusters for Mars missions use heat transfer principles similar to our fireblower, suggesting applications for melting Martian ice into water or fuel, a key step for colonization. Climate change adds urgency. OAA's 2023 climate data shows heavier snowfalls driven by warming-induced storms, demanding faster, smarter removal methods, while some experts doubt the timeline, citing risks of thermal runaway where flames melt more than intended. Advances in cooling technology, like those used in fusion reactors, pulsing coolant at gigahertz rates suggest control could be feasible by 2040. But dangers loom. Large misfired flames could ignite buildings, release CO2, or destabilize local climates by injecting massive vapor clouds, potentially intensifying storms. Preempting skepticism, fuel costs seem astronomical, but portable fusion reactors, projected by ITER to be viable by 2035, could power compact fireblowers efficiently. This future ignites a sense of wonder. Harnessing fire to conquer winter could clean cities, fuel space, exploration, or even terraform distant worlds. But it demands careful stewardship to avoid catastrophic overreach. What's your dream fireblower inventions? No clearing drone or Martian melter? Share your wildest idea in the comments, and it might spark a sequel. Finally, let us set your imagination ablaze with a speculative scenario that's daring yet tethered to physics. It's 2045, and you're in Anchorage, Alaska. After a record-breaking blizzard dumps 3 meters of snow, paralyzing the city, enter Maya, a maverick engineer who's gone viral on X for her DIY torch experiments, now unveiling her prototype, the Firestorm, a flamethrower forged from graphene ceramic composites, funded by a global crowdfunding campaign that exploded after her calculations hit millions of views. The Firestorm's nozzle, inspired by Fusion Lab tech, uses laser-guided plasma jets to deliver 500 kilowatts of focused heat. Maya flips the switch, and a meter-wide snowbank vanishes in a 20 degrees Celsius inferno. Steam rising like a geyser, but funneled into high-tech capture tanks to prevent flooding. Scaling up, she deploys a truck-mounted version, clearing an entire city block in minutes. The flame, powered by clean-burning green hydrogen, leaves no carbon footprint, and the captured steam drives turbines, lighting up 10,000 homes in a single burst. Crowds cheer as roads reopen, emergency services reach stranded residents, and Anchorage breathes again. But chaos strikes. A miscalibrated jet superheats a frozen water main, causing a steam explosion that cracks a street in half. Maya's AI controller, processing petabytes of thermal data in real time, adjusts the flame's intensity, shutting it down before disaster spreads. The tech catches fire globally. Rural Alaskan villages use firestorms to thaw wells, restoring water in hours. Antarctic research stations adapt them to carve ice tunnels, and lunar bases, inspired by NASA's 2024 plasma research, use scaled-up versions to melt regolith for habitats, paving the way for moon colonies. The physics checks out. CFD models show 20% heat loss to air, with the jet dissipating after 100 meters, avoiding atmospheric damage. Thermodynamics balance, with hydrogen's high energy density, 120 megajoules per kilogram, powering efficient burns. This scenario sparks, or could fireblowers power Arctic cities, fuel space exploration, or even send plasma pulses as signals to distant civilizations? The dual-edged salvation or inferno forces us to pause and reflect on our power to wield fire responsibly. Would you join Maya's fiery revolution, maybe as a designer or test pilot? Drop your role in the comments, and let's see who's ready to burn through the future. We've blazed a trail from snowy driveways to futuristic flames, weaving together burner specs, climate data, and AI-driven simulations to reveal the thrilling power and peril of fire meeting ice. What hit you hardest, the explosive steam geysers or the cosmic potential of fireblowers? Could we make this a reality without burning it all down? Share your boldest ideas in the comments. Your vision might ignite our next epic adventure. Smash that subscribe button for more physics-fueled journeys. Hit the bell for notifications, and share this with your crew to keep the fire alive. The universe is full of possibilities. Keep the spark burning bright. Until next time, stay curious, and let's set the world ablaze with wonder.